Merhaba Hülya.
Merhaba.
Nasılsın?
Merhaba Hülya.
Geçmiş olsun.
İyileşmemişsin
Teşekkür
ama
ederim.
herhalde daha tam.
İyileşmemişsin. Öyle mi?
İyileşmemiş daha tam.
Geçmiş olsun.
Teşekkür ederim. Henüz iyileşmedim. Ateşim hala devam ediyor
Ya
ama
bence sen kendini aslında zorlamana gerek yok ya. Bize böyle biraz kısaca basit bir şeyler anlat sonra bitir bence.
tamam.
Çünkü yani zorlama kendini çok bence.
Öyle yapayım.
Evet. Zaten buradakiler de yoruldu. Son konuşma ya. Son konuşması buradakiler de yoruldu. Daha böyle hikaye gibi bir şeyler anlat bize biraz. Hikayemsi bir şeyler. Tamam.
Tamam. Ben slide hazırlamıştım aslında önceden. O zaman slide'ları sana
Hayır, sen slide'ı konuşmak istiyorsan onu yap canım. Hani zor olmasın sana. En kolay olan konuşma neyse onu yap yani.
Tamam.
Kendini çok zorlama yapmak için. Hani
Kusura bakmayın ya. Böyle.
yani bize kusura bakça sen hasta olmuşsun yani. Yapabileceğin bir şey yok yani. Sen istemedin hasta olmak herhalde ya.
Evet. Bir 10-15 dakika o zaman slide'ların üzerinden geçeyim ben. Daha sonra sorusu olan falan olursa.
Aha. Yani çok böyle aşırı genel genel bir şeyler yap, söyle. Hani çok overall söyle, ondan sonra detaylara falan girme, yorma kendini.
Tamam, öyle yapalım.
Tamam. Slide'ları da post ederiz. Deriz bakın
yaparız.
slide'lara.
Tamam.
Yani gibi falan diyebilirsin. Ben size slide'ları tanıtacağım. Siz okuyun diyebilirsin falan. O tarz
Okey. Öyle yapayım.
Öyle bir structure yapabilirsin.
Tamam. Başlayayım mı?
Yok daha geliyorlar.
Tamam.
Konuşmalar hep okuyor, ondan
Tamam.
birazcık geç geliyor.
Tamam. Sorun.
They're coming soon.
Should we start?
Yeah.
Okay, maybe we'll start that.
Okay. Okay, we have Hülya Argus from Institute of Science and Technology, Austria. And she will talk about GHKS construction. And I should also note that she's sick and she's kind enough to give us a lecture. So
Yeah, she will summarize the slides for us. And you're gonna look at the slides by yourselves in the weekend because she has COVID. So,
okay, yeah,
she's pretty sick.
I'm sorry about this. Thank you very much for the invitation to this wonderful summer school. Special thanks to organizers. My plan is to just take 10-15 minutes to summarize the slides here, and I will stop afterwards. So if anybody would like to discuss anytime later on, next month or so, you're very welcome to contact me. So the talk is supposed to be about the GHKS construction due to gross-secking keel and seabed. This is a construction of an algebra of theta functions from a scattering diagram, and it's a very general construction. But in particular, if you consider the canonical scattering diagram due to gross and seabed, it provides a construction of the algebra of functions of the mirror in this case. So the paper essentially describes general scattering diagrams and then broken lines in scattering diagrams and how to use broken lines to define theta functions and to construct an algebra out of it. So to describe scattering diagrams, the first ingredient one needs to define is what is called an affine pseudo-manifold. This is almost like a manifold, but not quite a manifold. And the paper defines this affine pseudo-manifold in a pretty general way, which becomes more technical. But for the purposes of the conference, if you want to understand mirror symmetry just for low Calabi-Yau pairs, it's sufficient to consider a very special case, which is called a conical case. So they call an affine pseudo-manifold as conical if it is essentially a union of cones and you want some additional properties similar to toric fans and toric geometry, their generalization. And if you want to consider Calabi-Yau varieties which are not compact, then you cannot assume this conical, so the definition will be more complicated. The stereotypical example is if you look at the tropicalization of a low Calabi-Yau pair, it's a conical pseudo-manifold like this toric fan. In the easy case, if you just want to understand the mirror to a toric variety, then you just take this tropicalization, which is this affine pseudo-manifold, this toric fan, and the only additional data you need to fix is the monoid of integral points of the cone of effective curves. So you look at the cone of effective curves, effective curve classes, which is inside a cone inside the group of all curve classes modulo numerical equivalence. And then you define a PL function in a natural way in this cone by just specifying its kinks along codimension 1 locus. Like this is the fan of P1. The codimension 1 locus is just the origin. You specify a kink of a PL function at the origin by just saying, I want the kink to be the corresponding curve class of this codimension 1 locus. Here I draw a PL function, and once you specify all the kinks, such a PL function is not uniquely defined. It's uniquely defined up to a linear function, but what we do is we always assume, without loss of generality, it vanishes on one of the maximal cells, and this gets us a unique PL function. And then what is the mirror for toric low Calabi-Yau pairs? You take the upper convex cell, you of the PL function, of the graph of the PL function, and you read this as the momentum polytope of the toric variety, which is the mirror to the low Calabi-Yau. And what theta functions does is it gives a convenient way to describe the mirror. So if you view this as the momentum polytope of a toric variety, the associated toric variety will be like given by the equation xy equal t2p. And here I describe what the upper part of the graph is. And this is the mirror family in the toric situation. And then the ring of theta functions is generated by, so you look at the ray generators and their images here. So for smooth toric varieties, the ring of theta functions is generated by these generators. So these corresponding to these integral points, there are theta functions defined as I wrote here. And there's an easy, convenient way to write theta functions using what we call broken lines. They're combinatorial objects. So if you want to write, for instance, a theta function corresponding to this point, you look at a broken line coming from infinity, stopping here, and you say you start with a monomial because it comes from x inverse direction. It carries x inverse. So theta minus 1 will be x inverse because it doesn't cross any codimension 1 locus of the polyhedral cone. And at this point, again, if you want to write a theta function corresponding to theta minus 1, you again come theta 1, you come with a broken line coming from this direction, and it initially carries a monomial x because it's x direction, but it crosses this codimension 1 kink, therefore it gets a contribution from the kink, therefore theta 1 becomes x times the t to the kink. So they give us a relation, so broken line is just a convenient way. And we call them broken lines, and toric situations, they never bound. So you fix a point, you all look at the straight lines coming to this point from all the directions given by the rays of the fan, and they will generate a mirror. In more general situations, broken lines will bend. And before going to more general situations, I wanted to make a few remarks. So the kinks, specifying the kinks, is, as I mentioned, not going to determine uniquely piecewise linear function, but up to a choice. So I wrote for P2 3 different choices of PL functions, but if you assume it vanishes somewhere, then the choice is unique. And then you use the description of this PL function. It appears here in the definition of theta functions. And for P2, I wrote the mirror here with broken lines. Okay, there happened to be some issue with my, oh, I'm sorry about this. Apparently there happened to be some issue while compiling, so I think I will send you the slides, some definitions, and okay, don't appear. I will just tell you what appears. Some examples don't seem to appear. Okay, so in general, if you want to understand the mirror to a log Calabi-Yau, which is not a toric, you need to consider it's the associated affine pseudo-manifold, which is no more the toric fan. But if you blow up here, for instance, you will get, like as mentioned in the previous talk of Travis and Pierik and other people and Özgür, you have this column complex as a topological manifold that consists of 3 columns, but you can impose an integral affine structure on it by looking at the intersection pattern of the divisor. So here, when you blow up, the intersection, self-intersection of this number turns to 0. Here it's 1, 1. So how do we read the integral affine singularity at the origin? By definition, an integral affine structure is the choice of an atlas together with the data of change of coordinate functions. And you choose the atlas so for this example, just to give a concrete example of how do we determine the integral affine structure. So you take in R2 the fan of P2, and I couple it. So my first chart is the union of these cells, my second chart is these cells and these cells. And I have on self-intersection 0, 1, 1. So I map it toward this one to R2 with identity, this with identity. And because I have on 0 self-intersection here, this needs to be this map because, you know, by toric geometry, you can read the self-intersection number. So the intersection number of a divisor corresponding to a ray is the minus of, so if this ray is k times this ray plus this ray, the intersection number is minus k. And so you see, if you look at this, it's a focus singularity. In general, to understand the mirror, you need to again fix the PL function on these things. But once you fix PL functions here and here and here, if you look at the intersections, the PL functions, the values they take don't agree. So there is no globally well-defined PL function on all these things. But on each chart, different PL functions, we call it a multi-valued PL function. So similarly, in the toric situation, we fix the tropicalization, the cone of effective curves, the integral points on it, and the PL function. And I wanted to define a wall in the tropicalization, which was already defined in previous talks. It's a codimension 1 cell in the tropicalization. And a scattering diagram or a wall structure is the union of codimension 1 cells together with attached functions to them. And once you have such data, it was already mentioned in previous talks, you can do wall crossing. So if you attach here these functions, like they're elements of C double brackets T M, where M is the lattice, so it's the ring of power series with monomials of the form Z to M, where M is an element of the lattice with coefficients in the formal power series ring which generate as T's, where these T's have to do with the formation parameters, so I want to leave them having to do with curve classes, elements of the Morika. So I attach towards these functions, and then you can be, so you can understand once you have this data how you cross a wall, as also mentioned in previous talks. So there's a wall crossing algorithm, and in R2, if you have, if you forget about the polyhedral decomposition, you can describe a consistent scattering diagram, as mentioned in the previous talks, by just assuming you go around all walls and you get identity. This diagram is not consistent. You need to add this wall to check it's consistent. It's a first example, for instance, you can find in the tropical vertex paper of corresponder pandazi, but if you want to check. And if your polyhedral decomposition is not zero, where the walls intersect, which are called joints, if they lie in some, then that's the technical part of how to check consistency. There are different conditions to check consistency depending if your joint lies on a codimension 1 cell, a codimension 2 cell, or a maximal cell. And a good summary, I think, of this can be found, for instance, in our paper with Marcos in the higher dimensional tropical vertex. We outlined how to check consistency. Okay, and here I wanted to define broken lines. Apologies, I should have checked my slides in advance. I think we wrote a definition which we tried to simplify the definition in our paper, in our last paper with Pirik, we will talk about. So it's the broken line is a union of line segments with asymptotic direction. They come from infinity. So here I try to draw some conical pseudo-manifolds. You fix a point here. You want to come from some asymptotic direction and at this point. And each time you cross a wall, you bend. So a broken line is a union of line segments. And you impose on it some conditions, ensuring that each time you cross a wall, so it starts from infinity with C to M1, where M1 is the asymptotic direction. Each time it crosses a wall, it gets some, it changes, it carries a knee monomial, and this knee monomial is determined by the function attached to this wall. So it can change this monomial according to how the what the wall crossing function is. So once you write all your broken lines, you can define theta functions at a point P. So if you write all your broken lines ending at P, you can write theta functions ending at P. And on one definition of a scattering diagram being consistent is the algebra of theta functions being independent of this point. And once you have a consistent scattering diagram, then you have this algebra of theta functions. So one can show that the product of theta functions is a linear combination of theta functions with coefficients in K formal Pava series in the monomial Q, where K is a field. So using this broken line description, you can describe an algebra of theta functions. And I wanted to define the canonical wall structure here. It is a wall structure, so you take the tropicalization of low Calabi-Yau pair, and the walls, the codimension 1 cells, as mentioned in the talk of Pirik, are the tropicalizations of all A bunkers. And as an example, if you blow up P2 at one non-toric point, here is the canonical wall structure associated to it. If you write broken lines, here this one is misleading. I think I should just write from the XY direction. So there are four broken lines contributing to the generating the ring of theta functions. And yeah, I think this example is written better in one of my recent papers for explicit equations of mirrors to low Calabi-Yaus. It's all raised somewhat due to a compiling issue. So I think I would like to actually stop here, saying that to be able to write explicit equations for the mirror, you need to know the data of all A bunkers. I'm sorry. And so for any local with a toric model, what we did with Marcos is to find a combinatorial algorithm which gives you the data of all A1 curves, generalizing the Birkhoff corresponder upon the z-bit to higher dimensions that Pierik already talked about. And once you know the data, you can write explicit equations to mirrors. And I think I will edit my slides and stuff and send you a better version. Apologies for this. I think it's probably a good time for me to stop here.
Okay, let's start. Thank you very much. Any question?
No
Any
question.
short question?
Yeah, no question.
No question.
Any question, email her, she will respond to you. Yeah, that's okay.
Okay, thank you very much, William.
I'm so sorry. Thank you very much again. I hope to see you soon at some point at some other occasion. And thanks again to the organizers for this wonderful event. It's great what you're doing here. Thank you.
Thanks again.
Thank you so much. Bye. Okay, so the summer school ended. Thanks to the online participants.
Yeah, online participants, thank you.
Still participating.
You get the special prize, probably. Okay, so we will see you next week then.
Yeah,
At the
please come next week to the
Yeah.
conference.
Yeah.